刚刚稍微改动一下我的麦克风设定，有没有同学可以帮我测试一下？现在直播有没有声音？可以帮我测试一下吗？因为我刚发现它会收到我电脑风扇的声音，非常的可怕。可是我自己测又不准，因为我的声音太会被麦克风回去。哎呦，好 ，OK， 这样 OK。好，谢谢。啊，终于搞定了。
就是它好像功课它就会出现在物理的那个。
真的哦，好，那我回去跟那个助教讲。你是说功课的答案吗？好，我知道为什么，因为我一开始上这学期的课的时候，我也常常这样。然后一阵子之后，我发现，哎，不对，我好像对，我不知道为什么他们这学期开始以后，他没有把，对他没有把上学期的 link 拔掉，然后上下学期那个课号长得又，好像一个是5225，然后一个是5522吧，然后你看就，然后你就是会觉得长得都一样，然后你就会弄错。好，我等一下跟主教讲。来写个笔记好了。然后上下学期那个课号长得又，好像一个是5225，然后一个是5522吧，然后你看就，然后你就是会觉得长得都一样，然后你就会弄错。好，我等一下跟主教讲。来写个笔记好了。然后上下学期那个课号长得又，好像一个是5225，然后一个是5522吧，然后你看，然后你就是会觉得长得都一样，然后你就会弄错。好，你好。 我现在人在这边直播的时候，我不能开我的 YouTube 网页，哇，变得好大声，而且效果很不好。好，原来开直播还有这么多美角啊。OK， 好，so no, I just discovered that when I'm doing the live streaming, and sometimes I would like to check if my live streaming is working or not, and then I open my YouTube channel, and when I'm checking if my video is working, and when I'm typing, and I just find that my microphone here or my recorder here just take the sound, and then the sound gets so much amplified, and it's very not comfortable at all. Okay, so I just find out, that's so much hacks when we're doing live streaming. It's not as easy as I thought. Okay, so this is the announcement for our first midterm, and today we are here. This is the March 31st. Then we are going to have a long vacation, and after the vacation we are having the first midterm. Okay, and so this is we just keep the schedule this way. And then here are some instructions for the first midterm. We are still in a time that we should try to stop the virus spreading. So this time our first exam will be a take-home exam. So I will design the problems in the exam in a way that you can finish it at home. And you just finish it at home and then you take it back before the deadline. So this is how we do it for the first exam. And this is the ranges, the contents in our first midterm. So it's everything with electrics. So we are in electromagnetism, but the first midterm is all about electrostatics, actually. Yeah, electrostatics. We'll leave the electrodynamics later. So now this is everything about electrostatics. We have the sources and the Coulomb's law and the Gauss law, and we know how the force is distributed. So that is the electric field, and the Gauss law have two forms. One of them is the integration form, and the second one is the differential form. And then we talked about the potential energy stored in the electric fields. So this is the potential, and we are just applying the techniques of integration. And then we find a new definition that the electric field is actually the gradient of your potential energy, and we made the definitions. And actually in this section we are playing around with the properties of vector fields, scalar fields, vector fields, and we played a little bit about the divergence and curl and all of these properties. Yeah. And then we get into a chapter which is a little bit more difficult. This is in media. So this is like when the electric field is penetrating through dielectrics, or when it's penetrating through a conductor, and what is the physics happening there, and we try to describe everything that happens inside. Then we try to check if the Gauss law or the other physics laws or other mathematics tools that we develop is still working or not. And here for the dielectrics, we just find that because of the polarization of your dielectrics, then the actual electric field inside the strength, decreased. And we also find that we can use that kind of property to create a electronic unit which is called capacitor. And here's the relation between the charges, number of charges, voltage, and the capacitance. Then for the conductance, we just started it last time, and today we are going to finish the rest. And we just said something about the properties. Yeah, we just mentioned that because the charges is moving freely in metals, in conductors. So in any ways, inside the conductors, then all the charges repel each other, and then they just distribute themselves on the surface. And inside the conductor, the electric field is always zero, and all the charges are accumulated on the skin. So this is what's going to happen in a conductor. And today we will first do some practice on the calculation and do some comparison between the dielectrics and the conductors. And then we are going to introduce the voltage, resistance, and current. Yeah, so this is what we are going to do today. And the ranges of our midterm just ended up here. Okay, and then this is how we do it. So on the 7th of April, next Tuesday, before 13 o'clock, I will upload the exam sheet onto our website on New E3. So the exam sheet will be posted on it, and then you can download it. Please print it and write your answers on it, and then staple the papers together and keep them together and do not let them fall over everywhere. Okay, and then you have 24 hours to finish your exam. So on the 8th of April, and before 13 o'clock, please give your exam sheet back right here in this classroom. So this is SA320, and I and our TAs will be waiting here for you, and then you just take the exam sheet back, and then we will collect them and check if everyone gave it back, and we're going to correct it. And of course, this is open book exam. You can use any kind of references that you need at home, and you're totally free on it. And actually, you can discuss it with a friend. Honestly, I encourage you to do it, and you just finish it everything at home. But discussion doesn't mean that you can copy the answers, okay? So discussion and copy has a big difference. Okay, and so here are two rules. So the first one is like if we just find that multiple exam sheets, somehow the answers on it are just exactly the same, and then all of them will be rejected, all of them. We are not going to ask who is the original one and who is the copier anymore. Sorry, we don't ask it anymore. And we just give all of them back and reject it. And in this semester, there is no makeup. So you won't have a second chance to cover it anymore. So be really careful. Please just finish your exam sheet by yourself. You can do some discussions, but you should write the answers in your own way to do it on your own. Okay. And then the second rule is if the exam sheets are not stapled, if they are not bonded together, and it will be rejected too. Okay. And the deadline is nothing to doubt. Okay, so here are the regulations. And the important things I just repeated again in Chinese. 所以这是我们第一次期中考。那我们会在4月7号，也就是下星期二的中午1点钟以前，我们会把考卷电子档的，我们会把它上传到 New E3上面，然后请把电子档下载下来，然后请你把它印出来，然后请你把答案写在考卷上面，然后请你把你的考卷订起来，因为应该会有3到4张 A4 纸这么多，那请你把它订起来。那么你有24小时的时间写你的考卷，所以请你在4月8号中午的1点以前，然后请你把考卷带到教室来，就是 SA320。那老师会在这边等，然后那个助教也会在这边等。我们会把考卷都清点清楚以后，然后才会离开。然后呢，我们就等到1点钟。那么1点钟之后，我们就不会在这里了。好，然后呢，这次是请你在家里写考卷嘛，所以你可以使用任何你需要的 任何需要的工具书，任何你需要的工具都可以，甚至你用电脑 simulation 软体也可以。好，然后呢，同学之间的讨论是可以的。对，那我也觉得我其实蛮鼓励你们互相讨论。那你们互相讨论之后，还是要请你独自一个人写考卷。好，就是不要有那种一群人答案都一模一样的状况出现。对，所以我还是觉得讨论跟讨论之后消化，然后用你自己的语言写出来，还是有段距离啦。所以请你还是写考卷的时候，你要用你自己的语言写。然后呢，这个学期的规则跟上学期大致上一样，但是有一点点改动。就是如果我们发现有很多份考卷上面的答案长得都一模一样，这个时候我们会把所有的考卷都退回去，我们不收。那我们这个学期不会再特别去问说，谁是原创的，然后谁是 copy 的，copy 的人要不要补交等等。就这学期我们不会再特别问的。对，那宣导期已经过了，所以我们就是会全部都退回，我们不会再特别问。那么再来是这次要请大家就是把考卷都钉起来，以前都是助教帮我们钉，但是现在就是你自己印的话，请你自己钉起来。那没有钉起来的话，那我们也不会收。那你可能就是赶快回宿舍把它钉好，然后再挪回来。所以请你记得要在宿舍里面先钉好，然后再拿过来。我们在这边不会特别准备文具去处理那件事情。好，然后再来是最后就是我们等到1点钟，对，等到1点钟我们就会离开，对啊。然后那之后如果什么打电话或者写 email 给助教的话，我们也不能收了。好，所以这个是请大家要注意时间，然后请不要抄袭，对，所以我们的规定是这2个大原则。好，那有问题的话就在直播的那个留言栏留言好了。就我发现这东西其实还蛮好用的，虽然我一开始有点排斥。对，有问题在这边留言，那么也可以写 email 给我们，或是613有留言的功能吗？没有，好，613没有留言的功能，好吧？哦，好 ，OK， 了解。好，那么我们今天关于考试，关于时程。我再看一下我有没有什么要讲的事情。没有。好，那我们就开始上课吧。今天要小小赶一点进度。希望我们今天可以开始讲一点点词学。好。但是既定值还有好多没有讲完。上次我们讲到。好，那我们今天就不做复习的，我们就直接开始讲。Okay, so here I will start the comparison between the conductor and the insulator. So this is a spherical ball with charges deposited on it, and now because it's a conductor. So all the charges just stay on the surface of the sphere, and we just did the derivation before by applying Gauss law, or if you're not afraid of the complications, then you can try to use the integration with Coulomb's law, but we will get the answer like this anyway. So if I'm standing here and if I'm measuring the strength of my electric field, and I will get something like this. This is the dependency. This is always 1 over r squared, and r is the distance between the center of my sphere and my position. This is the total number of charges deposited on the sphere. So this is an electric field from a spherical conductor. But now we are, because of some technical reason and some theoretical reasons, and actually we are quite interested in this. So if you get yourself very, very, very close to the sphere, and you can imagine if you are like, if you are very little, when you are standing just on the sphere, and this is very convenient if someone needs to do numerical calculations or someone needs to do analysis on arbitrary shapes. So that's the reason why we do kind of zoom in. We zoom in into the sphere, and it's like we focus on a very little section of your conductor, and that's the reason why we are interested in a small section like this. And now the charges are they just stick themselves on the surface, and here we don't have any charges, because if you look down, and that is just the center of your sphere, and suppose we don't have any electric field inside, and all the charges will be on here, and no charges will be here, because they would like to keep away from each other as far as possible. And if we just focus on such a small pieces of your conducting sphere, just pay attention. The whole is a sphere. Okay, it's not a sheet. If it's a sheet, then it's another thing. But now it's just a piece of the sphere. And if we just apply the Gauss law, and what is the answer for the electric field? So now we just create a cylindrical Gaussian sphere, and the sphere on the top of your shell is A, and here is another surface. This is inside your metal shell. So just based on our observations on the Faraday's cage, and we can have a image like we have the electric field going out this way, but inside the sphere there is no electric field at all. So if we apply the Gauss law, this is Gauss law, this is the flux, so electric field and the area, and then we do the total iteration, and the charges wrapped inside the sphere is this one, and you have to regulate the number a little bit with the dielectric constant. And in this cases, suppose the electric field is evenly distributed. So the electric field strength, the area should be equal to the surface density of your charge multiplied by the area. This is the Q right here, and it turns into this one. And the others are not changing. And then this is the electric field strength of the electric field from a metal sphere, from a closed metal shell, something like that. Yeah, but of course, if it's a stick, and if you're looking at the total thing, but not just the sphere, if you're looking at things like that, like this, and then if you apply the Gaussian surface, like wrap it up like this one, and then you will get an answer like that anyway. But now we are focusing on the small pieces like this. So that is the reason why we have another answer. This is the answer that we just would like to focus on the surface charges and how it affects the local electric field. So that this is something the students always get confused. So I just try to make it as clear as possible. 这里我用中文再讲一次，就是这在课本上面有这个桥段，那很多人都会跑来问，因为描述在一般描述的方法里面会让人觉得很困惑，那我大概把比较常见的困惑都说明清楚。好，所以如果我们现在是有一个金属球壳，然后在那个金属球壳上面，我们有比方说透过什么摩擦法啦，或是什么用根棒子等等的，我们把一些电荷传送到我们的金属球壳上，然后很快的这些电荷就会很均匀的分布在球壳的表面。那他们会想要分布在表面，是因为他们彼此之间会互相排斥，然后彼此之间想要距离的越远越好，这样子它整体上它的电能才会是最低的。这时候，如果我们在意的是这一颗球壳整体，然后这时候如果你要使用高斯定律的话，你要做的事情是创造一个高斯曲面，封闭的哦。你要把整个球都包起来， 然后这时候你用高斯定律算出来的电场就会是像库仑定律的形状，它就是1除以 r 的平方 ，r 是你本人到球的中间之间的距离，然后呢这边是一个总电荷，你去算上面一颗一颗你总共有多少电荷，这是你跳脱出来哦，就是你如果你现在在意的是一整颗球的时候，然后你的高斯曲面包的是一整个金属球的时候，但是因为一些在理论上的理由，还有一些技术上，尤其是数值化模拟的时候方便的理由，我们很多时候会非常在意在一小段表面上面那么一点点 piece 上面，然后呢，你的在那边很 locally 的，就是我现在只关心这一小段的时候，那我的电场到底是多少？那你现在先想象一下，你先用那个缩小灯照你自己，想要把你自己缩小。你可以想象你是一只蚂蚁，然后你现在是站在这颗球的表面上面的一个点，然后这就是你感知到的东西。你现在站在的是球壳上面小小的一段，然后呢，这些所有的电场对你来讲看起来都好像是平行的。那这个时候，我要怎么样用高斯定律把那个垂直于表面的电场把它算出来？所以呢，你现在在意的就只有这么一小段的金属壳，就一小段。然后呢，所有的电荷都会附着在球壳的外层，然后里层是没有的，因为你可以想象，这个是一整个金属球的一小段，然后在球的内部这边是不会有电荷，就跟我刚刚说的，电荷它们彼此间互相排斥，它们的距离越好。那么你也可以想象我们上次讲的那个 Faraday's cage 就会变成在金属的球壳里面其实是不会有电场的。所以呢，你如果只看那么一小段，你看到的图像应该会是这个样子。那么我们在这个时候如果使用高斯定律的话，然后呢，你的计算方法就会是这边的细节我就不说了。然后呢，我们现在大概可以想象你的电场应该是 evenly distributed， 就是你电场的强度应该每个地方都一样，不会忽大忽小，除非，好，我们先不讲除非。那如果所以这边是只有一面会有电场的 flux 穿出去，那所以这个是电场的强度乘上总共的面积是 A， 所以这是 flux。然后再来是表面电荷的密度乘上面积，这个就是高斯面包进去所有的电荷量。然后呢，是因为这样子，而且我们要注意的是，你在意的如果是一个金属状的壳，或是金属的某一个体，但是你只看那个一小段、一小片表面的时候，你的电场是只有一面，就是 single sided。你一般的壳是这样嘛，然后壳会有上面跟下面，但是这个时候你的电场是只有从上面出去的，这是 single sided 的意思。所以你的电场强度应该是 sigma 除以 epsilon 0。好，所以 so this is the case for a metal, and this is always confusing because if you compare it with the electric field from an insulator, so now this is again a sphere, but for example this is made of plastic, and here are some space charge deposited inside the insulator. And how? Okay, I'm not quite sure how, but we just think about it and let's just think what's going to happen. And if we apply the Gauss law on such a spherical body, and supposedly we are going to have exactly the same answer. So this is just 1 over r trained, and this is the total number of the charges that wrapped up inside your Gaussian sphere. So if you look at it from outside, if you're looking at everything as a whole. The difference between, you don't see any difference between a conductor and an insulator. Though actually the distribution of charges are different. The distribution of charges in a conductor will be always on the sphere and nothing inside. With an insulator, it could be the distribution usually depends on the defects inside. 通常啊，就是如果你是一个 insulator， 可是里面却有 charge 的话，通常是因为里面有一些晶格缺陷之类的。好，但是如果你现在在两种材料上面，但是你关心的是一整个球体的时候，那么你使用了高斯定律，或者是你用库伦定律去做整体积分的话，你得到的答案都会是这个，就是你的电场的强度到最后只会跟全部的总电荷，还有你本人跟这个球体的中心间的距离有关系。But the difference is here. If this is an insulator shell, and if the charges are distributed, evenly distributed inside like this, and now first thing we have to notice is that the electric field is pointing out of the sphere and pointing into the spherical shell like this. So now the electric field is double-sided. 但是在一般介电子的状况底下，如果你是一个球壳，那你的电场就会变成会往外指，也会往里面指。所以这个是金属跟介电值最大的不同。那这个时候我们算出来的 flux 就会是电场的强度乘上2倍的面积。然后呢，这个就是一样，就是总电荷，然后最后你电场的强度就会变成 sigma 除以2，然后 epsilon 0。通常大家如果是在看课本的时候跳着看到这个跟这个，就会觉得很模糊了，到底是怎么样？关键就是在于说，其实它是一个整体。然后我们在这里我们看的是一小段，好，那么大家就不会说觉得为什么这两个不一样，那为什么这个跟这个又不一样 ？So usually students get confused if they somehow they read this one and understand this one, and then they read this one and understand this one, but it looks very conflicting and very confusing. And if some students are comparing this one and this one, and they get different answers, they get confused again. So I just try to explain it as clear as possible that we are focusing on the same thing, but we are focusing on different areas. Okay, so that's the reason why you get different answers. This is our first comparison. And then this is difficult, but we're going to do it. So this is the electric potential and the electric field of charged conducting sphere. And now we are doing the detailed calculations. We are going to do a measurement like this. We start from the center of your sphere. Sorry, this is small, but I don't have that much spaces on my slide. So we start from the center and we walk this way. So we just pass through the sphere, get out, and we keep moving and moving. When you're moving this way, but we are measuring the strength of the electric field and the voltage at the same time. So what is the trend of the strength of your electric field and the trend of your potential energy? So we just do a calculation like this way. 所以在这边我们要做一个实验，我们从金属球壳的中心出发，然后呢，你这样子走，从中间，然后穿过金属球壳走到表面，然后从表面再继续往前走，然后你一边走一边测量电场的强度，还有电压的强度。好，我们来做这个，我们现在先理论上计算一下。 So we start from the electric field strength outside of the sphere. I just described it in the previous slide, but now we are doing the real calculation. So this is how we apply the Gauss law. So Gauss law, no need to mention, and the flux. Now this is a spherical sphere, so the total area is 4 pi r squared, and this is the total flux, the total charge divided by epsilon 0. Okay, so this is easy. And we just rearrange the equation here. Then we have the strength of the electric field, and this is just the Coulomb's law when you are outside the sphere. So R is your position when your R is much, much larger than A, and A is the radius of your sphere. Okay. And when you're inside the sphere, then your electric field just drop to 0. And if you draw the plot to graphically represent what happened here, and it should be like this. So this is from the center, and this is, you just get away from your sphere, and inside the sphere the electric field strength is 0 on the sphere, and suddenly it just go to a very big value, and then it drops down dramatically. The trend is 1 over r squared. So the trend is very important. And I really recommend you to remember the 2 plots inside your head. This is very practical when you are working in the lab. Okay, and then we go on with the voltage. This is a little bit complicated. So usually people get stuck here because of the signs, the positive or negative signs, and who is minusing who, which is the reference and which is the measuring point, and people always get confused. I get really confused too, but this is my version, and this is the way that I always do it right. So I just share it with you. 这个计算电压其实它在计算上没有困难，但是通常大家会因为正数号的关系，或者是因为我要把我的参考点 reference point， 就是我电压是0的地方，我到底要放在这里还是那里等等的，大家会有困惑。那你去网络上查的话，会有很多种解法，课本好像也有课本的解法，但这个是我自己觉得最舒服的解法，所以这边我跟大家分享，给你参考。好，那么so in my work, I set my reference point on the V infinity, which means that when I am very, very, very far away from my sphere, when R is approaching to infinity, I set my reference point, voltage is equal to 0 right there. 在我的坐标系统里面，我设定当我离球很远很远很远的时候，我把那里的电压设定为0，所以这个是 V 无限大 ，V infinity R 等于无限大的时候，我把我的 reference point 放在那里，这个 ，and this is when R is far away from my sphere and my voltage should approach to 0. Okay, so when I am outside of my sphere, the voltage difference between my position and the reference point, so this is my position and this is a reference point, the voltage difference between them should be the electric field inner product, my pathway, and this is a minus sign because this is work, and work setback for potential energy, then we should have a minus sign. That's the reason why I have a minus here. And my integration started from far away to where I am. From far away to where I am. From the reference to where I am right now. Okay, so this is the logic behind it. 这边我特别讲一下。 就是你的电场乘上你的一小段移动的距离。好，然后这个是 work。那但是 potential energy 嘛 ，potential energy 它其实是你把那个 work， 你把这个 work 你等于塞过去，有点像时光倒流一样，你把你的 work 再灌回去的时候，你那个才是 potential energy。然后这个倒回去，时光倒流倒回去的动作，就是你前面要加一个 minus sign。然后呢，我在计算这股能量的时候，我是从我的 reference point 开始，一直算到我现在所站的地方。好，所以这条公式会这样子写，是因为这样子。通常大家会 confuse， 是因为你的 reference point 不知道设定在哪里了。好 ，and then the electric field, and when I am walking, the ds is actually just on the radial direction. I'm not walking this way. It doesn't change the answer anyway. So this is like, okay, so this is the vector form of my electric field, and this is how I walk. The inner product of them is always cosine 0 is always 1. Okay, so it doesn't make any strange result. And this is the constant K, E, and Q constant, and the integration of 1 over r squared is giving me a minus 1 over r, and minus give me a positive sign. Okay. And here's the ranges from infinity to where I am right now. And if you do the detailed calculation here, then if you put the infinity here inside, then your voltage is 0. Okay, so now the trend is 1 over r.通常在最后一步，大家会吓到，就是你会又再一次 confuse。通常是因为这里，就是你的1除以 r 平方，在积分以后会变成负的1除以 r， 然后呢，你积分得到的符号跟原本的符号就负负得正。好，这也是一个大家常常会很痛苦的地方。那最后一步就蛮简单的，你就是常数1除以 r， 你的趋势就是1除以 r， 并不会有什么很 surprising 的变化。那么这边是你现在所在的位置跟你的 reference point。那你的 r 变成无限大的时候，你分母也很大，所以你的整体就会越来越接近0。好，然后你如果是画在图表上面的话。If you draw the curve on your graph, then you will see that this is from the radius of a sphere, and the trend right here is 1 over r. And if we focus on the voltage inside your sphere, then now we set the reference point on the surface of the sphere. So this is the voltage on A, the voltage here. Now this is weird. This is our new reference point. And we just do the same integration, the electric field and integration, sorry. Okay, it's okay, no problem. So now the electric field inside is 0, but actually, sorry, I just need to give you a notice. The integration of 0 here, can I just take it as a constant? Yeah, actually it's giving us a constant. Oh, no, it's okay. So the 0 dot, yeah, we don't have any electric field inside, and then if we do the integration, then we have a 0 anyway. Okay, yeah, that's right. Sorry, I just a little bit confused myself. Okay, but the voltage from VR, this is where I am inside this shell, and the VA is the voltage on my shell. And if I don't feel any electric field, any forces, which means that the potential energy is not changing at all. Yeah, so that is a little bit more straightforward. And this is showing right here. So the VR, if you move it to the other side, the VR is equal to V on the position A, and it should be this one, KEQ over A. And the potential energy on the surface is the same as the potential energy at the center of the sphere, and there is no potential difference, then it doesn't create any electric force, and then you don't have any field. Okay. 我刚刚自己在看那个 integration 的时候，我突然有一点困惑，这样跑出来它会是常数吗？那个常数是0吗？我想一下说，哦，对，应该是0，没错。好，然后呢，那它在这边比较直观啦，就是我们如果不要被数学的套来套去困惑，你比较直观的去想，就是你在球壳表面上面的电压 VR， 它等于球壳里面的电压球壳里面的电压 VR 等于球壳上面的电压等于 VA 的时候，就是你的电压没有任何改变，等于是你的电场的潜能在这段距离上面并没有任何改变的时候，潜能一样就没有力，没有力就没有电场，所以这是比较直观的想法。那你就可以知道说，我的 VA 然后一直到里面 VR 全部都是一样的数字。那么它们就会等于 KE 然后 Q 除以 A。那如果你画成图的话，你就会看到这样。好，然后usually I will think backward again. If I have a voltage and there is no voltage difference, then if I take a differentiation on it, I get 0. That's fine. And if I have a 1 over R trained, and if I do a derivative, okay, 1 over R get into 1 over R squared, okay, then this is fine, and then the trained looks okay. 通常我看到这个的时候，我会再反向工程一次，就是如果我拿我的电压，然后我去思考一下它的 slope， 我去想一下它的微分，就是如果我是一个常数，常数的微分等于0 ，OK 没问题。然后1除以 R，1除以 R 的微分是1除以 R squared， 然后多个 minus sign。然后呢，但是你这样子你去微分之后，它会得到它的 trained 是1除以 R 平方 ，OK， 这样没有问题。好 ，OK， so this is how it works on a conducting sphere. And then, I just leave it right here for a few seconds, and then we're going to challenge the dielectric sphere. Then we're doing the same thing for the charged insulating sphere. 所以我们在对那个带电的绝缘球体，我们来做一样的事情。So the electric field outside such a sphere is just the same. This is just Coulomb's law. So this is fine. But the electric field inside is different now, because if you are standing on different positions, then the number of charges wrapped by your Gaussian sphere will change. You have to think about the volumes wrapped inside your Gaussian sphere. We just calculated before,
So I'm not repeating the steps anymore, but you can check it out. I think it's in lecture one of the two. 我记得应该是在我记得应该是在投影片那个1至2里面，我好像有做过这件事情。但是如果我们在算的是一个绝缘球体内部的电场的时候，它的差异就在于说，你现在电荷的分布是均匀分散在整个球体里面。那么你如果是站在这里的话，然后呢，你用个高斯封闭表面把这一块包起来的时候，它里面的电荷量会不一样，它会电荷量是根据你包起来的体积有多大而决定的。Therefore, we have to do this one. This is 4 and 3, and pi a squared. This is the total volume. Yeah, total volume of our sphere. And here is just a am I doing something strange? Is something missing? 看这个，你挥手，我怎么觉得有一点怪怪的？拍谁？等我一下。对啊，我觉得好像怪怪的呢。稍微等我一下。等我一下。所以上面是 rho 没有错，然后呢，如果是但是我要取的是里面的面积，我要取的是体积，体积就是4/3 派 r 3次方，这是 Q 1。对，这样没错 ，Q 1，然后呢？flux 乘上面积会等于它，然后这里是1a4 派 r 平方，所以应该要是 q r 3次方除以 a 的3次方。4派 r 平方，看一下最后答案是 a3。好了，最后答案对了。OK， 好，对不起，我太神经质了。好，没问题。是。Okay, so that's fine. Sorry that I'm a little bit too nervous. The final answer is right. 好，没问题。Good. So, okay. And now if we look at the strength of the electric field inside, then Now the trend is a little bit strange. Now the trend is growing linearly. It should be 0 at the center of the sphere, and it's just growing proportional to your distance to the center of the sphere. 所以你现在看电场的强度的时候，就会发现它的趋势比较奇妙。它的趋势是从0开始，然后会呈现线性的增长变大，直到你抵达介电球的表面为止。好，所以这是外面的电场，这是里面的电场。那外面的电场，它的趋势就跟我们刚才的计算是一样的，所以我们就不再特别重复。那么我们最后会得到的分布，它就会是E 除以 R， 它的趋势会呈现这样的走势。然后那我们现在因为在球壳的里面，我们现在是有电场的，那所以我们就会变成说，你的球壳里面的电压就会不一样喽。Now we are calculating the voltage inside the dielectric sphere. Now we have electric field inside, so we have supposing that we are having the voltages inside. So again, we are taking the reference point on the surface. This is where I am, and this is the electric field strength that I've just calculated here and here. And let's take all the coefficients. This is the constants that just move it outside. And if we do the integration of R, this is always giving you 1, so it doesn't matter. And if we do the integration on the R, then you will have 1 over 2 R squared. This is the result of your integration. And here's a minus sign. Just follow the equations.
像不是 A3方程式，因为那个排好像，因为三分之四排3方在分，就是分折，然后下面那个有一排，因为这样好像排就小掉，所以它好像答案会是 A3方程式 KQ。
我看一下。你说的拍是，我有点没跟上，我没听懂你的。
就是那个1 inside 那个，
对，
它是 Q 除以3分之4派 A3哦。
对。
然后它分母是3乘以4分之1派 K。那这样的话，它的分母应该有派平方。
分母
1的分母全部加起来分母应该有派，就是这样算出来的话会是就是它那个拍就是小掉，所以应该不会是A3。
拍会消掉，
会消不掉，
消不掉，
因为应该
会吧？拍上面是一个拍，下面也是一个拍。
可是上面那个拍是
我听懂你对，那边对，我听懂你的意思了。好，那我这个可能要改一下，你等我一下，我看一下，好，我觉得应该是这个公式打错了，可能是我在 copy 公式的时候，我可能有一些，我看一下，对，我可能是在 copy 公式的时候，我可能有写错字，我换成我现在写在那个黑板上的版本好了，请大家等我一下。还是老实来好了。
所以这是高斯定律，这样应该是 OK 的。然后再来是，但是我们现在的 Q 是在里面的 Q， 然后呢？用 Qi 表示是里面的，那这个 Qi 它就会等于density 是 Q， 然后对不起，它会变得有点复杂。4，这个是4除以3派 r 三方。然后呢，总体积是4除以3派 a 三方。所以这样是在里面的 charge 嘛，然后下面的 epsilon 是没有改变的。好，那我这边乱七八糟的，我就可以可以先消掉吗？应该可以先消掉。好，然后再来第二步，我们要换 a， 我们要把面积算出来。这边的话，3/4派就没有了，那么你这边就会变成只有，对，派上下两个也会消掉，所以它现在会变成 r 的3次方。除以 a 的3次方，然后 epsilon 0没有改变。然后呢 ，a 的话就会是4，对不起，4派 r 平方。好，到目前为止应该 OK 嘛？然后4派 r 移到下面的时候。就会变成，好复杂，等一下，4派，我要把它移动到这里，所以这个就没有了。这样，好。然后呢，4派 epsilon 0会变成4派 epsilon 0/1会变成 k。我通常是喜欢把它留着啦。等一下，让我停下来观察一下。这样，然后呢，现在会变成所以这边是有一个 r 在分子 a 三方不变。然后它会消掉，所以这个是 r， 然后呢它消掉，这样，好，这样对吧？然后再来是所以这个是 k1。好，这边改成 K1 Q over， 然后我把它拿到外面，这样子它的 dependency 看起来比较清楚。好，所以这是电场的强度，然后 V inside。 好，所以这个等于这个，这样应该 OK 哈。好，终于写对了。好，我应该是在把我旧版的投影片改成新版的时候，我可能打错字了，所以刚刚有一点多出一个奇怪的阐述，这样才是对的。Okay, so thanks to the reminder from the students, now the derivation is correct. I thought maybe when I was copying my functions from my old slide, maybe I just made a typo, so the terms inside the old equation is not right, and now the derivation is right if we do it this way. Okay, wow, it takes quite a long time to do it. Okay. So, okay, then it should be fine. And now, okay, so the trained R is right, and we do the integration, then it will be 1 over half R squared. Okay, so the derivation is right, and we start from the reference point A to where I am, R. Okay, so if I do and this is the VA. And VA, we move it to the right hand side, and this is just what we get. Yeah, so the trained is R squared. And if we draw it on the graph, here this is continuous, it shouldn't make a big step function like that. And this is the trained R squared. Okay, should be correct this way. So now the voltage here is going with the polynomial trained. Good. Okay, so if we do the comparison, you can see that for the charged, for the conducting sphere, and this is voltage is not changing at all, but for the dielectrics, now the voltage is changing, and it will be increasing if you get closer to the center of your sphere. Okay, and here's the comparison for what we have. So for the electric field strength, if we have conductors and if we have insulators, and the electric field distribution is 0, it goes up and then it goes down like that. And here's the trend. And if we have insulator, and this is a 0 at the center, it grows linearly to a maximal value, then it drops down. But sorry, I should change. I should regulate the size, the scale of my plot a little bit and make them exactly the same. Okay, but anyway, they just if the static charge inside is in the same amount, then the trend should be exactly the same. And if we focus on the potential energy, then for the voltage there should be a constant, and for the insulator then it increases and goes up. Yep. But if we look at the distribution outside of the sphere, and they are just the same. 所以你现在就是经过了一连串令人混乱的计算。对啊，坦白讲，那2张投影片，我每次要备课之前，我都要花个1-2个小时，重新检查一次，然后每次检查都还是有错误。So if we do the comparison, and this is the conductor and insulator, and you can see the trend and can compare the difference. 所以现在就是我们来做个大总结，大总结就是这张图。那你看导电的球体跟不导电的球体，然后你可以看到它们电场分布的不同。那你会发现，其实主要的不同点是在球体里面，在球体外面的话，其实它们两个的行为都是一样的。Okay. And if we go on, yeah, so we can have a little bit of rest here, and because we are starting a new chapter. We just did a lot of work for the static charges, and now we are starting a new topic. So this is when the charge is moving.
And this is leading to a new concept. This is the electric current. But here is the model. We start from the results that we measured from experiment. We are not starting from the theory. We start from the measurement, and we start from what we get from the experiment. So now this is the model. If we have electric charges moving inside a conductor, so we have positive charges, they are moving inside a conductor with a velocity. So D is for drift. So now the charges is drifting inside the conductor, and the velocity is a vector D. This is the cross-section, the area of the cross-section of the wire, and this is a distance that our charges moved. So it moved, and this is the delta x. Now here is the derivation. If I would like to know the number of charges passing through my wire in a certain time interval. So this is the number of charges that passed by, and this is the time interval. And now we have to do some calculation. So this is the density of my charge. This is the volume density of my charge. N is the volume density, and Q is just the amount of charges for a unit charge, and the delta x, here's a little bit of derivation. So the delta x, this should be your drift velocity multiplied by your time interval. So Vd delta t is equal to del x, and your delta x multiplied to A is just the volume. So this is giving you the volume, the total volume. And this is the density of charge. And the density of charge multiplied by the volume, then you have the delta x, delta q. This is the total number of charges passed by. And this is the time. Okay, a little bit complicated. But we go on with it. So now the time just doesn't matter anymore. It has a time in the numerator, another in the denominator, then it doesn't matter anymore. Then the averaged, we just define it, and then we call it current. So the current is actually the charges passed by a certain of cross section, and it depends on the width, the thickness of your wire, and it depends on the drift velocity of your charge. 所以其实电流的 modeling 其实是非常的 empirical， 非常的基于大家做实验的经验。那么我们经过这样的推导之后，你就会知道电流这个东西它有两个要素。第一个要素是我的电荷在金属里面往前游动的时候，它的速度到底是多少？它的漂移速度到底是多少？然后再来一个是你的 wire 本身的面积，好，所以这是基于实验，然后大家建立起来的模型。And then here, we need to define what is conductance. So this is the current that we just derived, and if I divide my current with respect to the area of the cross-section of my wire, then I have the current density. So this is our current density. Then based on our experiment, this is an experimental result. We just find that somehow the current density is proportional to the electric field that we applied along the current. And we just call the scaling factor conductance. So this is how we do it. So if you apply the voltage on a wire and you measure, okay, this is my voltage, higher voltage, and this is my lower voltage, and VB minus VA, and supposedly VB time. This is the difference between the voltages, and if I do a gradient on it, then I will have the strength of my electric field, and I just find this number is just proportional to the current density. This is my experiment, and 所以呢，这个是大家在做实验的时候发现的。大家就发现说，如果我有一根导线，然后一端的电压是 VB， 另外一端低一点好，这是 VA。然后如果我去取一个电压的梯度的话，我就会得到电场的强度嘛。那做实验之后，大家就发现，我的电场的强度会跟电流的密度成正比。然后呢，这个就是正比的常数，然后我们就把它叫 conductors。So if the conductance is larger, then I have larger current density. Okay. I insist that I just emphasized many times, and this is an experimental results because I'm sure some people will get confused if they are very clear about the theory. So you can see that the current is related to the velocity of the charge, and the electric field is a force. So usually the force is directly related to acceleration. But why is this force now proportional to the velocity but not the acceleration? Isn't it a little bit strange? And then I'm sure some people will say, is it alright? This is not theoretically alright, but this is experimentally okay. So the answer is, it's a constant velocity motion if you think about what we learned in the Newton's law. So if something is moving in constant speed, then it's not experiencing any forces. And the cases in our current is because that when the charges are moving inside the wire, they are feeling the frictions. And that kind of friction is leading to the concept that we have resistance R. So finally, they are moving in a way like they don't feel any forces from the electric field, and they are just moving in a constant speed. And even if we have something like a superconductor, or we have something like when the conductance is really, really high and when the resistance is very, very low, but the electrons is moving in a speed very close to the speed of light, but it's not going to be faster than that anymore, because when it's moving and it's radiating some energy out of itself, so the charges are always moving in that way. Okay. 所以可能有人会觉得不对啊，我们在牛顿力学里面的时候，我们有先界定过，就是所谓的力，它造成的一定是加速度，电场就是力嘛。那为什么我的电荷在一个电场里面的时候，它并没有加速，而是以一个的速度在运动呢？这样不是有点奇怪吗？答案是第一件事情，在一般的状况底下，那是因为我们的金属里面它是有电阻的，其实跟 conductance 也是连在一起的，就是那个电阻它扮演的角色就是一个耗散，像我们讲这个摩擦力一样。那么本来应该是要是加速的电荷，它被那个摩擦力的阻碍，然后到最后它们达成一个平衡的终端速度，所以它就是以等速度移动，好像没有受到任何力一样。所以这是第一个一般状况下面的答案。第二个状况就是假设你的电线是一条超导体，上面没有任何电阻，然后或者是你的电线就是电阻非常的小，那你的电荷它是速度是会变快没错，可是它一边在往前跑的时候，只要它的速度越接近光速，然后它就会不停的从它的侧边 垂直于它运动的方向，它会一直不停的发散出电磁波，然后那个发散出去的电磁波就会把它的能量耗散掉。所以其实是在那种状况底下，这条公式就是电流的强度跟电场的强度成正比，这条公式还是适用的。好，所以这个是关于电场怎么会只造成一个速度运动，而不是加速度运动，这个是完整版的解答。好，然后再来，here we're going to define the resistance. So here are some trivial derivations. It's not very complicated, so I just leave it for yourself. But the thing is, now the key point. This is the electric field, and this is the length of my wire, and the voltage difference is just the E multiplied by L. So I have a delta V, and delta V is equal to J over sigma. This is current density divided by conductance. Okay, so this is delta V, and where does the I come from? Sorry, I feel okay. So this is a J, and J we just turn it back into I over A. Yeah, that's it. And then we rearrange it a little bit. Then we have the voltage difference. This is easy to measure. So this is a voltage difference, and this is the current, and here is a new constant. This is the resistance. 电阻就是这么来的。好，然后再来这条就是欧姆定律，这大家都知道的，它不会很复杂。所以欧姆定律 ，so this is the Ohm's law, and this is not very complicated. I suppose everybody knows it. So that is the voltage difference divided by current. Then we have the resistance, and this is widely used in every kind of applications. Okay. Yeah, and here's a table for some common materials that the table shows the resistivity, the resistance. So here's, I focus on this one, and just a short reminder, if the temperature goes up, and usually the resistance goes up too. So every time when you're giving the resistance, and you have to tell them what is the temperature. This is very important. And here are some, usually copper is used a lot in electric circuits. So this is 1.7, and usually this is the reference for us to compare big or small. So silver is a little bit smaller. Gold has rather larger resistance. Aluminum is large, and usually in industrial applications, we are always struggling on choosing copper or choosing aluminum to use the material. But then the point is, if you use aluminum, you have bigger resistivity, you have bigger resistance, so usually it creates more heat, and it creates, so you need bigger voltages to drive your circuit, and it could lead to some problem. So usually higher class products use copper. 通常啊，我们在做那个技术上面的应用的时候，大家最常会纠结的问题就是你的电线你要用铜还是用铝？对，那通常比较高阶的产品会用铜。那用铝的话是它的问题就是说它的电阻比较大，所以你如果你的产品是用电流驱动的话，那你就要加比较高的电压。那如果不是的话，那铝本身因为它电阻比较大，那所以它也很容易发热。
然后那个发热就会变成一个问题。那么所以通常我们是比较低阶的产品我们会用铝，然后比较高阶的会用铜。Okay, so which one? And usually we like silver a lot. 如果说是真的需要什么速度快，低电高讯噪比，就是你如果那个电路的 noise 要很小的话，我们通常会选择 silver，silver 是更好的选择。And yeah, usually that's it. And you can do some comparison with, this is conductors and this is insulators. So silicon, this is semiconductor, and glass, this is conductor, insulator, so insulator is usually in that range. And you can see that, wow, that's a big difference between them. Okay, 差不多是这样。So, here is something I just said it again in English. And usually when we are designing the circuit, and if we have the need that we want the noises of you want the signal of your, the signal strength like this. And if you want to have your noise as low as possible, usually we would choose silver for the products aiming to the highest class of the quality. Because if you use silver, then your resistance is very, very low, so it's easy to drive, and it doesn't create that much heat, so you don't have that much electronic noises because of the temperature. But the problem is, silver is very, very expensive, and it's soft, so if then it's not very robust against all kinds of scratches or all kinds of bending. Yeah, so good materials in electromagnetism is bad materials in kinetics. So, 通常状况就会是这样，对啊，音哦，就是它的电性很好，但是它的机械性质、力学性质很难操作。所以这个是我们大家常常会觉得很烦恼的问题，就是银，因为它非常的柔软，然后你如果把它弄在电子电路上面的话，它很容易会剥落，所以这就是很麻烦的地方。通常一个材料如果它的电性很好的话，然后它的机械力学性质就不太有，这个就是我们在做 design 的时候常常会觉得很 suffer 的地方。好，这是关于电阻。好，那么so this is a summary more or less for today. Okay, we have 15 minutes left. And now finally we just put in the information for conductors. So here is one thing, more than the zero electric field. Now we have the Ohm's law. So this is the voltage and the resistance and the current. And if you have the big tables, and then you can just fill it in and finish it. I will ask you to give it back with your midterm examinations. So if you finished everything in a very nice way, then you get bonus on it. 所以还有很有纪律的、很持续性的在填这张大表格的同学们，你们在写完那个 take home exam 之后，把你的表格跟着你的 take home exam 一起交回来。就如果你准备得很好，然后很有纪律的从第一步一步慢慢走到这里，这做得很完整的话，就会帮你加分。然后学习是一个纪律的过程，这么多东西可以撑到现在不容易。So let's just rest for a while.
这边先小小休息一下，让大家把那张表格完成。最后应该会让你们看一点影片，看一点持续的影片。好，我现在想让你们看哪个？好，看一下。在场的同学看起来都差不多了。So if I look at the students in the classroom, seems like everyone is ready. And now I am switching to the videos. So we will start the physics in the lecture after the midterm. But today I just would like to show you a little bit of videos and do a little bit of relax and just give you a taste as a start for magnetism. Okay, so let's watch the first video. Although the subtitle is in Chinese, but I suppose if you look at the pictures here and if you look at all the motions here, then you understand what's going on. It's okay. The subtitle is not really
ガウス加速器と呼ばれる簡単な実験装置を紹介しよう。レールの上に並んだ鉄球に同じ大きさの鉄球をぶつけてみる。このように一番反対側の鉄球だけがぶつけた球と同じ速度で転がる。いわゆる運動量とエネルギーの保存速というやつだ。では今度は鉄球の列にネオジウム磁石という強力な永久磁石を加えてみる。すると鉄球はインパクトの直前、ネオジウム磁石に強く引きつけられて瞬間的に速度を増す。その分だけ弾き出される鉄球の速度も速くなるというわけだ。ではもし仮にこの磁石の力を極限まで高めることができたとしたら一体どうなるか。弾き出される球の速度もそれと比例して超高速になる。つまりこの小さな鉄球がライフルの弾丸になる。これは超電導加速器。超電導電磁石の強力な磁力を利用して今からそれを実証しよう。
所以这边是他告诉你一个磁铁，这边他做了一些特别的，它有一些特别的功用。我今天先不要解释好了，下次再解释。So this is a simple experiment and telling you the strength of a magnetic field. But here is a chain of physics interactions when he's playing around it, and I'm explaining it in the next lecture. So here is another video for you, showing you different kind of mechanisms in materials.
might not think of water as being magnetic, but it is, and so are graphite, aluminum, and glass. This is a new and different category of magnetism called either para or diamagnetism, and it's different from the magnetism that you're used to. You're probably already familiar with different.
好，我这边说一下 here I just stop for a while and because here I'm sure you need Chinese translations. 这边要特别跟你说的是就是磁性物体，除了像我们刚才说，我们刚刚看到那种是很明显的铁磁性的物质，就是它在遇到磁场的时候，它会被极化，然后它也会跟磁铁一样产生一个北极跟南极，然后会产生磁力。但是其实那只是其中一种物质而已。第二个物质我们可以再把它做一些更细的分类 ，ferromagnetism。ferro 就是铁的意思，任何跟铁有关的，或是任何会很强烈的被极化产生南北极的东西，我们都会叫它 ferro 叉叉叉 ferro 叉叉。So ferromagnetism, ferro is everything related to iron, but more than iron, ferro is related to everything that can be strongly polarized by magnetic field. So ferromagnetism is the material which is very strongly correlated with magnets and magnetisms. And here are other categories. Paramagnetism. Para is everything which is walking along, or something which is very acceptable against the magnetic field. 就是顺磁物质啊，然后任何就是我不知道这是哪里的字根，但是只要任何事情它是会很顺应外界的变化的，我们通常都会给它冠一个字根，就是或是前缀词，我们叫它 para。Paramagnetism 是顺磁性物质，然后 dia 就是作对、反对的意思，所以 diamagnetism 这个是反磁性物质。那物质我们磁性物质大概可以分成这三种：反磁性、顺磁性，还有铁磁性。然后铁磁性里面还有一个家族是，它一旦被磁性极化之后，它要花很久的时间，甚至永远它都转不回来，就是它没有办法恢复成那种没有磁性的状态。像那种东西，那个就是永久磁铁。那永久磁铁它算是在铁磁性物质里面的一个分支。那么事情会变成这样，都有它背后的理由。所以我会在第一堂课的时候会有点进度超前的，我会讲一点固态物理的部分，然后尽量跟你们解释为什么会发生这样子的事情。但是呢，我们在讲一大堆 microscopic 的东西之前，先让你们看一下各种不同的材料，然后在遇到磁场的时候的变化。
From the magnetism that you're used to. You're probably already familiar with ferromagnetism. Ferro means iron. An unmagnetized piece of iron or nickel or cobalt becomes a magnet in the presence of a magnetic field. The effect is strong and lasts even after the magnet is removed. Paramagnetism is a similar effect, except that it's much weaker and temporary. Aluminum is a good example of a paramagnet. And so is oxygen, which is attracted to magnets. Here, I have a few milliliters of liquid oxygen, which sticks to the magnet. I'll explain why later. Gadolinium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed. They would rather die than be in a magnetic field. An important example of a diamagnetic material is graphite. This specially made pyrolytic graphite is repelled by a magnetic field. Don't be confused. This is not static electricity or eddy currents. Graphite is repelled by a magnet, always, both by the north and south end. Pyrolytic graphite is a grown crystal of flat carbon layers which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite repulsion to whatever magnetic field is present when they're chilled. They are perfect diamagnets. The most famous and powerful diamagnetic is bismuth, element number 83 on the periodic table. The bismuth-powered boat sails toward the weaker magnetic fields. One way to check whether an object is diamagnetic or paramagnetic is to see how it aligns itself in a magnetic field. Diamagnetic objects like glass will rotate to avoid magnets. Here, we see that the glass is diamagnetic because it twists to get to the weaker magnetic field. But aluminum rotates into the field, typical of a paramagnet. On the periodic table, we see that aluminum has 3 valence electrons. So what does it take to understand what it means for something to be a paramagnet or a diamagnet? You have to know what the electrons are doing. Consider, for example, aluminum. We see from the periodic table that aluminum has 3 valence electrons. That's 2s and 1p. Now it's that unpaired electron that makes it a paramagnet. This unpaired electron enables it to become magnetized. And it's that unpaired electron that is free to be magnetized and attracted by the magnet. But what about a diamagnet like water? Yes, the water molecule. It has all of its electrons paired. It will not be magnetized. In fact, water is repelled by a magnetic field. The electrons come to lower energy as they are moved away from the magnet. In conclusion, when something is a paramagnet or a diamagnet, it tells you what its electrons are doing. In the case of a paramagnet, it has at least one unpaired electron. In the case of a diamagnet, it has mostly paired electrons.
How? So, if you're interested, you can take the periodic table and then you can look for those substances with a lot of unpaired electrons on the shell, and that is strongly magnetized. And if you look at some for example, like the lazy gases, and all of the shells are filled with the electrons, and all of the electrons are paired, one spin up, one spin down, and then we don't have any chances to turn it into a magnet. So that is strongly related to the electron configurations. Okay, we are going to talk about it later. So this is all for the lessons today, and I hope that you will have a happy vacation and a good luck for your exam. 所以我们今天上课就先上到这边，可以下课了。